Right, it should be noted that the first ideas that people have when they're talking about light is that they said the light is some sort of continuous spectrum. Light comes down, light's everywhere, light travels all everywhere, all the time, 100% of the time, everything is light, right? So this guy called Max Planck came along. Planck said, looked at this and said, no, I'm not too sure that this idea of continuous light is such a great idea. I think light is more discrete. He came up with the idea basically of the photon. Because he said that light travels in small, perceptible, immeasurable packets of energy, okay, which he called a quantum. And the quantum essentially is a packet of light. All right? People think about here about quantum theory and quantized. And I know some of you are looking at this going, quantum theory, I'll never be able to understand quantum theory. Well, if you think about quantum just means a very, very small amount, okay? So people are freaking out about quantum theory. I can't understand quantum mechanics. Why can't you understand quantum mechanics? Because it's got the word quantum in it, right? Quantum theory, all it means is that it's just a very small measurement. We're just talking about light and how it interacts with electrons. It's not too complicated, okay? That's why we teach it in general chemistry. It gives you a background for what you're going to study in physical chemistry. Quantum theory, how small packets of light are measured by taking, or you can measure the energy that's involved with them by looking at the frequency of the light. All right? So you look at that frequency value, and you come up with something that's called the H value. Okay? H here, this is Planck's constant. And Planck's constant, I can never remember, is 6.63 times 10 to the minus 34 joules. And it's not just joules, but it's joules per second. And the reason being is that in order to get this into energy, I've got to have a second value. Okay? So if I wanted to do this energetically, suppose I have 6.63 here, okay, and I want to find out energy. My frequency, this is in joules per second. My frequency has to be in seconds down here. So if my frequency, say, is 305, it's 1 over seconds. Okay? That second value has to cancel. Now my seconds cancel, and my unit that I'm going to be left with at the end here is a joule. And that joule indicates that I've got energy. I've now measured energy using Planck's constant. Okay? It's not going to be a lot of energy. I mean, look at this. 6.68 times 10 to minus 34. If you remember the frequency values of high-frequency light, for example, gamma radiation, gamma has a frequency of 10 to the 20th. So the most energetic light that we can get, 10 to the 20th, as far as orders of magnitudes go, is 1 times 10 to the minus 14th joules. That's really not a lot of energy. Okay? In the light world, that's a ton of energy. But as far as what we're eating, okay, one Cheerio is going to have more energy than that particular photon of light. Okay? So when we talk about light, and a lot of times you'll run into this in organic chemistry, when we talk about light energizing something, light is going to be h nu. So this is a shortcut we use to say light. So if you ever see h nu over an arrow or somewhere in a chemistry book, h nu is the representation that chemists and physicists use for light. Okay? It's just a shortcut that we use. All right. Now, the takeaway from Planck's idea is that as light comes in a quantum state, small packets of energy, these photons, when they come in and they hit, something interesting is going to happen. Okay? There's an experiment done where you have a positive source, a cathode, okay, and there is some metal that was associated with it, was associated nearby with it. What would happen is that light would come down, and as it hit, electrons would be emitted and shot onto the cathode. Now, if you know anything about movement of electrons, when electrons move, you've got electricity, right? So when this happened, we could actually measure a current. A current was measured. And this is the basics of all photovoltaic cells. PV cells, have you ever heard of that before? You should have. It's a solar cell. Okay, solar cells work this way. Light comes down, releases electrons, and electrons flow through the circuit. The light is forcing the electrons to leave, and in doing so kind of completes the circuit there. And that electricity movement is something that can be used to power something. Okay, so those are full photovoltaic cells. All right. Now the energy that's going to be used to figure this out, right? The kinetic energy of the light is going to be equal to h nu minus the binding energy that's associated with it. Now if you think about this in terms of solar cells, okay, here's kinetic energy. We like energetic light. We like knocking these electrons free. Okay, the kinetic energy depends upon the binding constant. How easy is it to liberate those electrons? Okay, that's what W means. We can use this to develop our solar cells. All right, and that's it for quantum theory, the beginnings of quantum theory right now. We'll get into a little bit more of it here in a minute.